I'm going to try to not make this too exhausting. At the same time, what I'm going to be talking about is one of our use cases and stuff that is slightly technical. My main goal here is to demystify machine learning. Right? So I think probably everybody here has heard about machine learning. Is that right? Is there anybody here who's doing machine learning? A couple of hands. Anybody has data science on their LinkedIn profile? Most people do nowadays. All right, so we're going to talk a little bit about big data-driven business innovation. I work for Pentaho, and Pentaho was acquired about a year ago by Hitachi. Everyone knows Hitachi. It's a company of about 300,000 people, and it's a company of makers. It makes parts for cars, projectors, TVs, and they make trains, and they're rolling out trains here in the UK. Now, in the past, the way trains worked in general is that you sold trains to a country or to a train operating company. And when that's your business model, your goal actually is not aligned to your client, is it? Your goal is to sell the maximum number of trains and have them break down as much as possible so you can maximize the number of trains and service needed, right? However, in fact, it's almost like a consulting business model, right? You want to develop things as slowly as possible. You want them to break down the maximum amount without getting fired, basically. However, if you're switching to train as a service, which is what Hitachi has done here, you're delivering throughput and latency. A certain number of people move from here to there in a certain amount of time. And when you're doing that, what becomes the driving motivation? Minimizing the number of trains, right? And if you want to minimize the number of trains, you have to worry about things like reducing downtime. And so there drops in one of the big IoT use cases we always talk about nowadays. Anybody know what I'm talking about? Predictive maintenance. It's kind of been the first one that keeps coming up in the IoT world, industrial IoT world. So you'll see here, the business challenge is to modernize and improve rail transportation reliability here in the UK. Now these trains, each one has about 3,000 sensors on it. 3,000 sensors. Those 3,000 sensors, they're operating at about 5 hertz, in other words, 5 data points per second. There's about 250 of them, these trains. So we're talking close to 4 million data points per second. It's about 100 trillion data points per year. That's pretty big data, right? And so that's when we start talking about Hadoop platforms. And the whole reason for using Hadoop is that it scales fairly linearly, that the cost is manageable. And so the use case we're talking about here has been, the technical side is anything as a service, XaaS, outcome-based pricing, right? Predictive maintenance is how we accomplish it, schedule optimization, and total asset optimization. These 3 things all have in common a technical detail. That technical detail is that they are mathematically known as NP-hard, which means, and this, by the way, is the whole reason machine learning exists. There's a whole class of problems that cannot be solved. If you had all the computing power available from now until the end of time, you would not be able to solve the problem. Tic-tac-toe is a simple problem. It can be solved, right? But chess is not. Chess is NP-hard. So we build machines that can lower the scope, the search space for the problem. They have heuristics, like a human being. When you step into the street, let's say there's a Ferrari bearing down on you. Do you take time to notice the weather, the time of day, the color of the car? No, you step out, right? How does your brain know how to filter things? Because other times you do notice the color, don't you? Those are machine learning heuristics. And that's the whole purpose of artificial intelligence and machine learning. It's to be able to filter out the search space for a solution, right? And so that's when we start talking about all these problems. They have that in common. They're all NP-hard, non-polynomial time hard. And of course, the other buzzwords around this, Internet of Things and big data science. By the way, Internet of Things, when I hear that, I think to myself, is data coming from anything other than a thing? Almost all data comes from thing. We've all been working in IoT for a decade or more, right? It's just now it has a marketing term around it. So the way I start with this is, we have to break these projects down into phases. Phase 1 is about smart connections. That's the sensor data. What we're talking about here is taking data from the physical world and moving it to the cyber world, right? Digitizing it. It might be continuous or analog data, but we're taking it from the real world and making it available to computers. Then we talk about converting data. This is data to information. Now, what do I mean by that? I mean, like, imagine you have a door of a train that's open, right? Now, that sensor is pumping out 5 times a second, door open, door open, door open, door open. Is that data meaningful? No. It's only meaningful in the context of knowing that the door has been ordered to be closed, or how long ago the door has been ordered to be closed, right? So that blending of data, that's where you start getting information out of data. And you probably all see this whenever we talk about data siloing, right? Everybody here faces that data siloing problem. That's why we have data integration tools, because data in silos tends to be less valuable than blended data. Then I talk about centralization. I don't mean, this has been misunderstood when I talk about this. I do not mean it all has to be sitting on one disk, on one server, in one scale-up platform. I really think these things should be scale-out platforms and distributed computing. What I mean is the data can all talk to each other, right? You can blend all the data together. Finally, I talk about cognition, and cognition is about machine learning. That's moving data from information. Data is up here. Information is here. I think of this as knowledge. Now we're talking about machine learning. This is how we relate data to each other. And then finally, CI, continuous improvement. That's about taking data from the cyber world and moving it back to the physical, right? Because all of that work you've done previously, all that knowledge and analysis and predictions and all those things are pretty useless until you find a way to do the business transformation. So we make predictions. That door is going to fail within 3 weeks at 90% probability. So we'd like to change the door or the motor or the actuator that, within the next 3 weeks while the train is in the depot. But there's a whole business transformation process around making that happen, right? There's a supply chain, inventory, getting the people there, and so on. So what I'm going to talk about briefly here, covering all of these in about 15 minutes. Each one requires a 4-year degree, but we're going to try to cover them each in about 3 or 4 minutes. Now, anybody here who's been working in data science knows that these are not discrete fields, right? But I'm going to try to separate them a little bit, and this is mostly for ease of understanding. What I'm not going to do is talk about reinforcement learning, actually, because reinforcement learning is less common. Has anybody here heard of Google DeepMind? Yeah, most of you guys have heard of it. This game, they're a little game that plays Atari games, right? So I'll talk just really briefly about this. Reinforcement learning is things like Google DeepMind, playing Atari games. It learns to play Atari, right? And how does it learn? It learns it has a bunch of inputs. It can go up, down, left, right, and the way it knows if it's succeeding is if the score is going up. Well, that sounds simple. The computer can just move forward and see if the score goes up. If it doesn't, go the other way. Is it that simple? Of course not. First, because the score doesn't go up right away in reaction. Also, sometimes it's a combination of things that makes it work. In other words, there's all sorts of features we have to extract from this unstructured data, and we have to understand time lags. That's why reinforcement learning is hard. Reinforcement learning at its core is talking about systems that are allowed to interact with their environment and perform their own experiments. All of you have dealt with A/B testing, probably. Anyone who's dealing with web interfaces has dealt with A/B testing. This is kind of a form of A/B testing, right? But the point is the computer narrows the search space because there are an infinite number of possibilities it could follow. But we want it to pick a certain number of them and drill down. I'll talk first about statistical models. And the example I'll use is ordinary least squares. Now, everyone here in the 5th or 6th grade or whatever you call it in the UK, 6th form, something like that, has done this before, trying to pick a best fit line. You have a bunch of data points. You have, let's say, your independent variable across the bottom, and then the one you're trying to predict in the y, right? Y equals something. I've put it in matrix form here just to be fancy. Y equals x beta plus the error term. Now, imagine you want to make predictions, right? Here we've seen these are all linear. In other words, x is to the degree 1. And we've seen how good predictors they are. We've seen down here that it seems to be a pretty good predictor, right? Here, does it look like it's a good predictor? No, this one probably should have x to what? What power? Probably the power 2, right? This one, we're not sure. Are these good predictors? Are these really telling you much about what's happening? Not really, right? And this one, you can just tell that your data is very sparse. So the problem, what is the drawback of straightforward statistics? The main drawback is actually to operate most of the methods. This is, by the way, why we have machine learning. Most of the methods you want to use, like OLS, require that you know what's called the functional form in advance. You have to know what the formula looks like, and all you're going to have the computer do is figure out the coefficients, the numbers in front of the polynomial. That's the main drawback. Now, this is great if you're trying to get a Nobel Prize and you want to understand everything about the system. But in the commercial world, are we doing pure research? No, we're not trying to find out the fundamental nature of reality. We're trying to find out how things are related. So things like deep learning are great at making subtle distinctions about how things work, but they're not great about surfacing why that is. But the why isn't usually necessary. So that's a drawback in statistics. You have to know a lot of information before you even get started. But let's talk about supervised and unsupervised learning, really. Each one I'm going to give a couple of minutes here. And when we talk about supervised learning, what we mean is we know what we're trying to predict. We have data from the past of that prediction, right? So let's say we're operating trains. We have data from running those trains, and we have failure data. If we have failure data, now we can make predictions. Now, there's all sorts of subtleties in that data, but the fact that we have source data and what we call target data, failure data, means all we need to do is figure out the right formula or the right approach, artificial neural networks, recurrent neural networks, CNNs, and so on, to tie them together. Now, in unsupervised learning, we don't have target data. We don't have something we're trying to predict. What we're trying to do is find intrinsic structure. You've seen this in basket analysis, for instance, in the retail world. Sometimes you have some goods that you want to find out how they relate to each other. But if it's two products like spaghetti and spaghetti sauce, you'll find out they're complements. They get bought together. Whereas maybe one type of spaghetti and another type are substitutes. Either one or the other gets bought, right? Now that's really simple. You can do that straightforward statistically. But if you have thousands of products, all of a sudden it becomes a very complex problem, and you start looking at unsupervised learning methods. Again, you don't have target variables. All you're trying to do is discover intrinsic structure in the data. That's what unsupervised learning is about. So machine learning, supervised learning. You've got all your source data. In this case, we have structured data and unstructured data. You might have data coming from your ERP, from your point of sale system, your CRM, your enterprise asset management, and so on. And you want to find out, you want to pull out, much of it might be unstructured, right? It might be social media. It might be sensor data or log data. Now, how do we move data from unstructured to structured? We do a task we call feature extraction, because you know what? No matter what a company tells you about processing unstructured data, that's not what they're doing, right? The whole task of being able to work with unstructured data is translating it to structured data. So we take that unstructured and structured data, we put it together, we create what we call feature vectors. This is a task we call feature extraction. And now we take that data with the labels, the target data, and we run it through algorithms. We use algorithms like naive Bayes classification or support vector machines or convolutional neural networks and so on. And we come up with a model. And then we deploy that model online, right, in the actual real-time system, real-time, near real-time, et cetera. The system has data coming in for which you want to make predictions. Does that make sense? Or am I just talking and to myself? Kind of, some people nodding. So that's typically what we do in a supervised learning model. In an unsupervised learning model, what I've shown here actually is 6 panels, 6 generations of an unsupervised learning model. So most models, they evolve. You run them through thousands, millions, billions of generations. Of course, a billion generations take 5 seconds or something like that. But what you're trying to do is evolve the system, right? That's when we say artificial intelligence and machine learning, we mean the system learns, gets better over time. So in this case, I'm using the most common possibly the most common clustering, unsupervised learning method. Has anybody heard of k-means clustering? Looks like a decent number of you. The core idea behind k-means clustering is we throw a bunch of data. You'll notice that the data is all the same. The colors are different, and these little stars are in different locations, but the data is all the same. And that's the generation 1, 2, 3, 4, 5, 6. The data is all the same. But over time, the stars are moving. What k-means clustering about is about finding internal structure. Now, in this case, we have two variables. So visually, we can see structure. How many clusters do you think there are? What does it look like? Somebody say something. 4, right? It looks like there's about 4. Now, of course, that's sensitive to what you think, what is a real cluster in your business. But it looks like there's about 4 clusters here. One of the drawbacks with k-means clustering is that you actually have to put the number that you want, which is fine if it's 2-dimensional. It gets a hell of a lot more difficult if it's 1,000-dimensional, doesn't it? There are techniques like scree and random forest and other methods you can use to reduce the dimensionality. But you can see here what the system does is over time, it starts at a random spot and slowly tries to figure out through what's called a gradient descent learning where the center of each cluster is. And guess what that does for you? I mean, intrinsically, it's not obvious why this is important, right? But what happens over time, in this final generation, we're probably not that happy with this one, right? What looks wrong here? It looks like 2 of them got stuck over here, and it sounds like, it looks like that's a result of the initial random state they were set in, right? They didn't evolve properly, which is why you actually do these millions of times. You do not just one generation evolving 1,000 times, but you do 500,000 generations, each of them working separately, right? And so then you pick the one that best fits the model. Now, what ends up happening, well, fine, it's fine to have this, but what use is that? You know what? Now you can detect anomalies. Because we said supervised learning is when you have target data, when you know what's going to happen. So if I'm running a train and I don't know, if I hadn't, we deployed the trains this year. Have those trains ever failed? I hope not. If those trains have never failed, do we have failure data? No. So can we use supervised learning? Not really. So this is all about so what we can use this for is anomaly detection. Understanding what happens in the source system, in the train, and what are the normal ways of functioning, so that when something happens that's way, let's say a standard deviation, 2 standard deviations from one of these stars, now all of a sudden we know, bam, there's a problem, right? So I'll tell you where I usually start. This is all fine, and the problem we usually have is we just gather all of that data together, and we say, hey, what can we do now? That's probably coming at the problem in the wrong way, right? I usually say, what could I do if I had perfect, universal, and timely information? When I say perfect, what I mean is that the data is good quality, right? It's real. It's not from 3,000 broken sensors. When I say universal, I mean that there is no excuse with the cost of communication technologies today for you to say that there's some piece of data that's unavailable to me. Every piece of data available anywhere in the world to any company is available to you. You might have to pay for it, but it is available. So anything that's knowable, you should have available to you. And then I say timely. I don't mean real time. I mean available at the time you want to make your decision. So if you have those 3 things, now you can start where, it doesn't make sense to come the other way. Oh, let's start with a big data system and now we can get started, right? No. We start with it by saying, if I had all the information in the world, what could I do? What could I imagine that the system could do? What techniques would I apply? Those techniques I was talking about a moment ago, those are the problem-solving techniques, which you then put into a business transformation. All this other stuff, Hadoop or data integration or whatnot, that's tooling. That's not the key part, right? The key part is this question. And with that, that's it. I tried to avoid getting too technical. Does anybody have any questions? Guess not. Thank you.